Remember, there are different types of chemical bonding. We dealt with this a little bit when we dealt with naming, but we really need to understand these differences. We have ionic bonding, covalent bonding, and metallic bonding. Ionic bonding is that cation anion attraction. It involves an electrostatic attraction between oppositely charged particles. So one species has gained electrons, one species has lost electrons, and now those positive negative charges are attracting. Covalent bonding involves the sharing of electrons, and this is typically observed between nonmetals. We say typically because bonding is really a spectrum. It's not really a black or white answer here. But again, covalent bonding typically seen among those nonmetal species. Metallic bonding is the bonding that we see in metals themselves. So it's the if you have like aluminum foil or iron metal or zinc metal, this is what's happening is metallic bonding. Metallic bonding has metal cations sitting in a sea or ocean of electrons. They call it the sea of electron model. It's typically what's observed holding metal atoms together. So the properties of the elements in the compounds are consequences of the type of bonding that's exhibited. Bonds form when they lower the potential energy of the atoms or ions. It's an exothermic process. Again, exothermic means energy has been released. We also need to understand Lewis dot symbols. I'm not going to spend a lot of time on these because we're going to be using dual Lewis structures, but you should be able to do a Lewis dot structure. Lewis dot takes the valence electrons that you have and you give the elemental symbol one dot for every valence electron. But just like when we're doing electron configuration or filling atomic orbitals, we do parallel before paired. We've keep that idea in mind so we don't pair up the dots until we have to. So like lithium has one valence electron, we see one dot. Beryllium has two valence electrons, we see two dots. Carbon has four valence electrons. We see the four here. Sorry, I don't know why it keeps doing that. The four here, we've got four dots. Up to fluorine, we've got seven valence electrons. We've got seven dots. Neon, eight and eight dots. So again, we don't start pairing up until we see them paired up here because we finally have to. We have four sides to that atom. We're going to write four dots individually before we pair up those dots. That is your Lewis dot symbol. Lewis dot symbols follow your octet rule. The octet rule states that atoms tend to gain, lose, or share electrons in such a way as to gain noble guess electron configuration. Most often eight. There are exceptions to this, and we will talk about the exceptions, but most species want to follow your octet rule. So again, I know I stated this already, but ionic and covalent bonding is a spectrum or a continuum. Ionic bonding is that electrostatic attraction of two oppositely charged particles. We have covalent bonding, which is the sharing of electrons. But what we find is we can further break this down. Ionic, again, electrostatic attraction, anion plus cation combination. But then within covalent, we have nonpolar and polar bonds. Nonpolar means equal sharing of the electrons. Okay, that's driving me nuts. Where polar covalent has an unequal sharing. Okay, we're gonna ignore it because it keeps doing it. Like my iPad's getting tired. Um, and you can see the joke down here, ionic bond. Hey Eugene, would you like a cookie? It just gives away the electron entirely. It gives away the cookie. Covalent bond. Let's split up a cookie 50-50. Equal sharing. Polar covalent bond, 7 ace for me, 1 ace for you, unequal sharing. To determine how the bond is going to behave, though, we look at the electronegativity of the species. Electronegativity and electron affinity are two different things. And we'll talk about that on the bottom here. But electronegativity is defined with the measure of how strongly the atoms attract bonding electrons to themselves. So the electrons are in a bond; they're shared between two different atoms. And how likely is it for something to pull those electrons towards itself? It does follow your trend of ionization energy, and the higher the electron affinity, the more electronegative that a species is. The difference between the two, though, electronegativity and electron affinity, is electronegativity is a chemical property. It shows us how well an atom can attract electrons towards itself, while electron affinity is defined as the amount of energy released when an electron is added to a neutral atom. So electronegativity is an unequal sharing or pulling of electron density towards itself, whereas electron affinity is it gained an actual electron. And you can see the trends here. Again, we told you that the trend follows ionization energy, so it increases across the table and up the table. Tendency of an atom participating in a bond to pull an electron density towards itself. What is the most electronegative elements and what are the least? Well, following your trend, you can see that like cesium and francium are the least. Fluorine is number one, followed by oxygen, then nitrogen, chlorine. You need to know the general trends, but you also need to know that first place, it's driving me nuts. I give up. I'm writing that. Okay, you need to know first place goes to fluorine. Second place goes to oxygen, and third place is tied with nitrogen and chlorine. So fluorine is in first. I'm definitely hitting my iPad somehow that I've never done before in the 4 years I've had it, and it's doing that, and I apologize. But fluorine is first, oxygen is second, and chlorine and nitrogen are tied for third place. After that, you can follow the trends, but you do have to know that the those species comparative to the rest of the species on the table. You have to know fluorine is number one, oxygen is number two, and chlorine and nitrogen are tied for third.